I do have to stay here because I have to charge my iPad. It was losing battery. All right, we're going to compare a couple things today, and that is reactions that go forward only with our reversible reactions. So whatever your two colors are for A and B, you're going to use those throughout the activity. Oh, I can pull the screen down. Thank you, Jocelyn. I'm going to use blue and green. Remember, when we do particle diagrams, we need to use a key. So we're going to start out by assuming we have 14 particles of A, and A is going to react to form B. So we're going to count these up. 8, 9, 10, 11, 12, 13, 14. And if this is forward only, then all of the A is going to form B. So I should end up with 14B. 11, 12, 13, 14. 14A to 14B. When we have a forward only reaction like this, we can actually describe it as saying it goes to completion. And that's because all of our reactants are going to be converted into products. This will also be true if we have a reaction where there's a limiting reactant and there's excess left over. If the reaction proceeds and stops, it goes to completion. Does that make sense? Okay. So when we have reversible reactions, they can go both ways, right? So we could show a forward only arrow if it goes forward only. Okay, we could show a reverse arrow if it goes reverse only, but what we're going to do is we're going to show them as an equilibrium arrow. Now, big connection piece here. What occurs in a chemical reaction that's at equilibrium depends on how quickly A converts to B and B converts back to A. This is our connection to kinetics. This is why we have to do the kinetic piece first. Okay, so before we go on to talking about equilibrium and drawing particle diagrams, let's remember and refresh our memories on what types of things affect reaction rate. All right, give me some things. Temperature. If we increase temperature, we're going to increase rate. Let's talk about why. Higher temperature means more kinetic energy, which means we're going to have more collisions, and that makes the rate go faster. Okay, great. What else besides temperature? Grace? Say that one more time. Catalyst. Whoops. C-A-T-A-L-Y-S-T. Okay. A catalyst is going to lower the activation energy. Whoops. E-A. Or increase number of collisions by providing more favorable conditions, right? We're going to increase activation energy by providing a different or lower activation energy, excuse me, by providing a pathway that has lower activation energy. Okay, great. What else? Yeah. The volume. Okay. Volume indirectly changes it. If I can spell today. Because by changing the volume of a container, we change what else about a gas? Yeah, Owen. Pressure, yes, but what else? Number of collisions. Yes, that's ultimately where we're going. Yeah, you guys are missing the easy one. Concentration, right? That's what I thought we were going to get first. Okay, concentration is usually what we think of, or at least for me, is what I think of first when I think about changing reaction rate. So by changing volume of a container, yes, it changes the pressure, but really it changes the concentration of the gas. Okay, so if we change concentration, whether it's a gas or if it's an aqueous solution, if we have a higher molarity, then we're going to have a faster rate. And yes, that is because we have more particles. Okay? Or in the case of volume of a container, we have more particles in a smaller space. Right? So that's going to give us more collisions and a faster rate. Okay, here we go. We're still going to use our same two colors, A plus B. But now, this is going to be a reversible reaction. So we're going to look at this stepwise. This is probably something you haven't done before, which is great. But we're still going to start out with 14 particles of A. So very first thing we want to do is draw those 14 particles of A. Here's 14A. Which means we'll also have 0B. And here's how we're going to use this. Obviously, on the left-hand side, we've got particles, particle pictures. In the center, we're going to describe both the number of particles of everything that we've got, but we're going to explain what's going on with the reaction rate. And then the last column here with the reaction direction, we're going to use this to quantify the reaction rate and then also use the arrows to qualitatively show what's going on with that. Okay, so I'm going to help you out on this first part, and then as we move forward, you can help me out with the rest of this. So what we've got here is just the forward reaction taking place, right? Does that make sense? So we've got the forward reaction is happening. We could even say this is the only reaction, and I'm going to use RXN to abbreviate reaction. Only reaction to occur. We can also say then it's the fastest. So if the forward reaction is the only one to occur for the reverse reaction, we can say no reaction because we have no B. Okay, I'm going to give you a forward reaction rate, and then you can help me with the rest of this. So if, let's say the forward reaction rate is 4 particles per second, what's the reaction rate for the reverse reaction? 0, great. Okay, so with these arrows, can we see how we have the arrowhead already printed out for you, but then it's a dotted line? We're going to fill the line to help qualitatively show the speed of the reaction. So for our forward only reaction, we're going to fill the line all the way to show the forward reaction going fast. All right. So now, if it's 4 particles per second for the reaction rate, and we're now at second number 1, what's going on? We've got 4A particles that are turning into 4B particles. Right. So we're going to subtract 4 particles of A, and we're now going to have 10A. And we're going to add 4 particles of B. So we want to draw that. 10A, 1, 2, 3, 4B. All right. Now what's going on with the forward reaction rate? It's going to be slower. Great. So we're going to say this is slower than before. And that's because we have less A. And then now the reverse reaction can start. Yeah. We're going to say reaction begins. B is present. Okay, so now we have to quantify that. What should the reaction rate for the forward reaction be at this point? If I had you start at 4 particles per second. Don't overcomplicate it. and it's going slower, we're going to make it 3. Okay. Now, on our arrow, to show that it's going slower, we're going to make the arrow shorter. What do you think the reverse reaction rate should be? Let's make it 1. Okay, great. And then we're going to make like a short arrow to show it's going slower. Okay, great. So now both reactions are happening, forward and reverse. They're happening at different rates. So we got to think about this for a second. All right, we have 10 particles of A, and now 3 of them are going to turn into B. Okay, so let's just start there. Let's go 3B, right? Don't draw anything yet, just hold on with me. If I used 3A, how many A are going to be left? 7, right? So I'm going to draw 7A. 1, 2, 3, 4, 5, 6, 7. Okay, how many B do I have still? I've got 4. And one of those 4B is going to turn into an A. So I'm going to add one more A. And then how many more B? If I took 1 away from the 4, I need to now add in 3 more. 1, 2, 3. Yeah. So the total number of A is what? Should be 8. 1, 2, 3, 4, 5, 6, 7, 8. And the total number of B is 6. We still have a total of 14 particles, right? Law of conservation of mass. We started with 14 and 0. Then we had 10 and 4. Now we have 8 and 6. Okay, talk to me about the forward reaction rate. It's going to slow down, right? Slower because we have even less A. Great. The reverse reaction is going to be faster because we have more B. Okay, so what's the value going to be for this based on how we're kind of quantifying this? Reaction rate for forward is going to go from 3 to 2 particles per second. Great. Make it a little shorter. And then the reverse reaction is going to go from 1 particle per second to 2. Awesome. Okay, great. So now we have 2 particles of A forming B, while 2 particles of B are forming A. So tell me about what we've got at second number 3. 8 and 6, it's going to be exactly the same. 8 and 6. Wonderful. Which means if we have the same amount of particles of A and B in second 2 and second 3, what's going on with the rates? They're going to be equal. Yeah. Same as before. Same as before. Which means 2, 2, and then we can draw our little arrows to finish it off. Okay, great. So here's the thing, in case we didn't know this, kind of our big key point. Chemical equilibrium occurs when the rates of the forward reaction and reverse reaction become equal over time. It is not when the amounts are equal, right? We've got 8 and 6. Those aren't equal amounts of reactions and products. It's the rate of the reactants forming products and products forming reactants being equal that makes this system be at equilibrium. Can we see how it happens over time where it evens out and they become equal, the forward and reverse? Okay, let's answer these questions on the next page to get this wrapped up, and then we can talk about our other couple new concepts for the day in this context. Okay, what's the reaction going to look like at 10 seconds? It's going to be the same, right? We're going to have we're going to have 8A and 6B. And why is that? Yeah, the reaction rates are equal. Therefore, concentration of A and concentration of B will be constant. All right, cool. We already kind of talked about 2 and 3. Why does the rate of the forward reaction decrease over time? We've got, let's do it this way. As A yields B, less A is present. So if we're talking about the reverse reaction speeding up, the opposite is true, right? We're still looking at the reaction of A yielding B. We've got more B is present. Okay. For question number 4, we're going to write a ratio of the amount of products to the amount of reactants. So we want products over reactants, which for us, let me make this bigger, is going to be B over A. So I just want total number of particles. So at equilibrium, how many B particles do we have? 6. And we have 8 A particles. So let's reduce this and make this 3 over 4. Is this going to change over time? No. This is at equilibrium. Therefore, concentration of reactants and concentration of products are constant. Okay, awesome. Okay, number 5, finishing this up. Here's a particle diagram for the same system, A at equilibrium with B, with this reversible reaction, but we actually don't know if it's at equilibrium or not. So that's what we need to figure out. How can we do that with this picture that we have? Because we don't have the same amounts, right? There's not 14 total particles here. Cool. Use the ratio. Okay, so we're going to have to count them. So how many A's do we have? 1, 2, 3, 4, 5 A and 2 B. So remember, we want the ratio of B to A. So we're going to say 2 over 5, which does not equal 3 over 4. Therefore, not at equilibrium. I will use that at EQ to represent and abbreviate at equilibrium, because I'm not writing that word all out every time. Okay, great. So there's part of this. Now, we need to draw a particle diagram of what it's going to look like while it's at equilibrium. But the first question we need to answer is, which way does the reaction need to go? Do we need the forward reaction to go more to make more products, or do we need the reverse reaction to go more to make more reactants? And how do we know? Sam? Why? How do you know that? Okay. B is a product. Let's use these, because we're not always going to have the pictures. So let's use this here. Yeah. Yeah. So if we're not always going to have the particle diagram, we are going to want to use, let me change colors here. We are going to want to use what we need to form to help us out, okay? So, because here's the deal, we're not always going to have a particulate representation, but the particulate representations, I hope, have been really helpful to conceptualize what it means for a system to not only reach equilibrium, but to stay at equilibrium. Okay, so what's our picture going to look like then? I'm going to make it really generic here. This one works out nicely, right, in terms of the number of particles you were given, because you were given a total of 7. So we are going to wind up with 3B and 4A. Whoops. So we're going to draw that. 1, 2, 3. 1, 2, 3, 4. 3A and 4. Whoops, rewind. 3B and 4A at equilibrium. Okay. Here's the thing. This is what we just did, even though we didn't use any of these terms, aside from chemical equilibrium. We explained and described and represented a system both approaching and at equilibrium. We wrote and calculated an equilibrium constant. We wrote and calculated a reaction quotient. We compared the value of the reaction quotient to the equilibrium constant to determine which way the reaction needs to proceed. These are all things you're going to have to do with equilibrium problems that you likely have had to do with equilibrium problems already, even though my guess is you just memorized what you were supposed to do and then did it. Yeah? So let's talk about each one of those couple of things and make sure that we understand what it is you're supposed to be doing. So if we look at number 4, in number 4, this is your equilibrium constant that we wrote, or K, also known as Kc for concentration, also known as Kp when you use partial pressures. Right. We use the law of mass action to write an equilibrium constant expression. We use the concentration of the concentration of the products raised to the power of their coefficient over the concentration of the reactants raised to the power of their coefficients. We omit pure liquids and solids since we cannot measure their concentrations. We can also write a Kp expression using partial pressure, same thing. Partial pressure raised to the power of the coefficient of the products over partial pressure of the reactants raised to the power of their coefficients. Same deal. Can't measure partial pressures of liquids or gases, or I'm sorry, liquids or solids. In this case, you wouldn't have an aqueous solution that you're going to measure the pressure of because you can't. Here's what I do want you to know, though. You are not going to give me any kind of fractional answer for an equilibrium constant. You're going to give me a straight up value, right? You're going to give me a number. Like in this case, we would use 0.75. And that value is going to give you information about what's happening in your system at equilibrium. So we already saw from our particle pictures and from our ratio of 3/4 that we have more reactant then product at equilibrium. If you don't have that particle picture and you just have a value, you need to use the relationship of K compared to 1 to help you with that. So if K is less than 1, like we have in this case, there's more reactants than products, at equilibrium. Which should make sense, right? When you think of a fraction or a ratio, if the larger value is in the denominator, the overall value is going to be less than 1. Right? In our case, reactants are in the denominator. So if our value is less than 1, we have more reactants. Opposite is true. If K is greater than 1, we have more products and reactants at equilibrium. And again, same thing here. Products are in the numerator. If the numerator is greater than the denominator, then our value will be greater than 1. The magnitude of that also gives you more information about it too. Like here, 0.75 is not that much smaller than 1, so we have a pretty close relationship between the amount of reactant to product with a little bit more reactant. Sometimes the opposite is true, and you have a really, really, really big K value because you have a lot more product than reactant, or a really, really small because you have a lot more reactant than product. Okay. All right. Last thing before we move into our graphing activity is looking at number 5, which is what we wrote as a reaction quotient, which Q-U-O-T-I-E-N-T, or a Q expression, or QC, or QP. You write them the exact same way you write a K expression. Products over reactants, you either use concentration or pressure, and you're going to raise those values to the power of their coefficient. The difference is Q is for any point, regardless of whether it's at equilibrium or not. We just don't know, okay? If unknown, if system is at equilibrium. So there's 3 scenarios. If Q equals K, what does that tell us? It's at equilibrium. Great. Wonderful. If Q is less than K, like we had here, we say that the reaction shifts to form more products. Therefore, you're going to increase Q to equal K. All right, let me say that again. If Q is less than K, the reaction shifts to make more products until the value of Q would be equal to the value of K and we reach equilibrium. So then the opposite is going to be true if Q is greater than K. We've got too large of a ratio. That means we have too much product compared to reactant. So the reaction shifts to form more reactant. Therefore, we're going to decrease Q to equal K. It's important that you understand the relationship to Q versus K, and you're able to explain it, not just because, again, My guess is many of you memorized these three relationships and what you were supposed to do and would have been unable to explain given a scenario. And that's okay, because we're going to work on it. Okay, now, let's not overcomplicate this, though. All right? When you learned greater than and less than signs for the very, very first time when you were little, how did you learn them? Alligators, yes. Okay, so we're going to, think about this for a second. If you always put Q versus K, okay, Q comes first. Okay, Q versus K, then your alligator is going to chomp the way your reaction needs to go. It's really silly, but it's going to help you remember it. Right? So if Q is less than K, the alligator chomps towards K, but K is on the right, so are the products. So you need to make more products to get Q and K equal. If Q is greater than K, you're going to chomp towards the Q, which is towards the reactant side. You make more reactant to get K smaller, or excuse me, Q smaller to equal K. Does that all make sense? I hope that talking about this through the context of reaction rate, the particle diagrams, is going to help you to be able to understand and explain equilibria and Q versus K and what needs to happen with that.